All right, this is going to be just some review questions. We didn't get a lot of time to do review questions in class. We spent time on that one problem, but I feel like that one problem is going to get you ready. So let's look at this first question. First question, we've got two blocks stacked on top of each other. There's going to be friction between those two blocks, but nowhere else, and they're attached to another block by a pulley. And what we want to do is find the acceleration of each mass if those two slip with respect to each other. So, to begin, so 1 will be the hanging mass, 2 and 3 as shown. To begin, we're going to do free body diagrams. Let's start with the little mass on top, mass 3. So with that, we're going to have friction pulling it that way because it's slipping, normal force up, and the weight down, and it's going to accelerate that way. No surprises there. For mass 2, things are going to get a little bit tricky. We have tension pulling that way, weight down, and then we have the normal force from the mass right above it pushing down. That's in Newton's third law of force pair. That normal force has to come from somewhere. And then we have the regular normal force from the ground pushing up. And then just like we had the normal force from the block above, we also have friction from the block above pulling in the other direction. That friction has to have a force pair that goes along with it. And then for the hanging mass, real simple, we just have tension up and weight down. Now one thing I really want to point out to you is that the tension attached to my two masses is different than the tension attached to a hanging mass because my pulley has mass. Okay, and we should be used to seeing this by now, so we're going to go ahead and do the diagram of the torques acting on our pulley. Now, torque 1 pulling over, torque 2 pulling down. And then, just to make things clear, that alpha is going to be acceleration 2, the acceleration of my coupled masses over R. And we'll need to use that later. So, we're going to take these. So for each of the first 3 free body diagrams, we're going to do Newton's second law. So for mass 3, Newton's second law, sum of my forces equals ma, equals friction. Let's go ahead and plug in what that friction is going to be. And we can get A1 right away. So looking at this, because it's slipping, it's not going to have the same acceleration as everything else. So we're done with mass 3. Now we're going to look at what's going on with the rest of them. Masses 2 and mass 1 are attached to each other. They have the same acceleration and it's different from mass 3. So if we look at mass 2, net force is 2ma, because it's 2m, and that's equal to the tension pulling forward and the friction pulling backwards from our free body diagram. So if we plug in what friction is, then we look at mass 1, it's mg minus T2. Now looking at that, we know friction, we know our masses, we don't know tension 1 and tension 2. So we need to go back over and look at our pulley, look at the sum of torques for our pulley. So we have I alpha equals the torque from tension 2 minus the torque from tension 1. So go ahead and plug in our moment of inertia for this disk. And as we solve for the acceleration now, all the radiuses cross out, and I have 1/2 ma equals tension 2 minus tension 1. So I'm going to put that as a third equation over there. And if I'm solving for acceleration, I'm just going to add all those together. So that gives me 7/2 ma equals mg minus the friction. And I'm just plugging in what we found for friction up above. No surprises there. So, solving for the acceleration, masses cross out, and my acceleration is 2/7 g times the difference between 1 and that coefficient of kinetic friction. Real basic, real easy problem. Second problem, we're going to take a pulley and we're going to have a complicated system attached to that pulley. We have two masses hanging off of one end. We're going to have one mass hanging off the other end. And they have tension 1, tension 2, and tension 3. Now, in the interests of time for this video, what I really want you to do is find tension 1, tension 2, and tension 3. But all I'm going to do for you right now is find the acceleration. It's up to you to find the tensions on your own and then check the video. So, I'm not going to draw free body diagrams here. We're just going to look at them each individually. So if we look at that 2m mass, we have 2ma equals 2mg pulling down, T1 pulling up, so we're going to make it negative, and T2 pulling down, so it's positive. That's my first Newton's second law equation. Then we'll do the same thing for the mass underneath of it, which should be easier. They're accelerating down, so ma is mg minus T2. And right away you can see what's about to happen with T2, which is nice. Then we'll do it for the third mass, which is accelerating up. So it's going to have T3 pulling up, which will make positive, and then mg pulling down. Now if we look at this, T1 and T3 stick around, but T2 goes away. So we also need to look at the ring, the sum of the torques on my ring, to figure out what's going on with T1 and T3. So from that we know I alpha is equal to T1r, because it's accelerating that way, minus T2r. Since it's a ring, it's just going to be a mass 2m, so mr squared times a over r equals my torques. And again, in this situation, there's no slipping, so alpha was a over r. All of my r's cross out, and it leaves me with 2ma equals T1 minus T3. Now I have a fourth equation to put over there, and it's going to make everything go away and behave nicely. So we'll just write it down right there. 2ma equals T1 minus T3. We're going to add all four of those together. So adding all the masses, I get 6ma. Then all my t's go away, and I've got 2mg plus mg minus mg. That's just equal to 2mg. So right here, we have the acceleration is g over 3. And like I said, you're going to have to go online to find out each of the tensions. Check each of the tensions. But at that point, you just pick an equation, plug in your acceleration, and the tension should pop right out. So, no surprises there. The next question, 3, is one that we've seen, again, before. And so for question 3, I just want you to find the acceleration. We've done this a bunch. I'm going to leave it completely up to you. So you're going to look online for that again. Sorry, I don't want this to take up all of your time. And then the last question is a rolling with slipping question. So in this case, we're going to roll it. We're going to give it an omega in that direction, and we're going to drop it on the ground. So we are starting off with an angular speed. We're going to put it on the ground, and what we want is to find the time where we reach the non-slip condition. Now, because we're slipping, alpha and a are not equal to each other. Once we stop slipping, then they both go to 0 and we travel with a constant velocity. But while they're slipping, they're not equal to each other. So we have to consider each motion separately. So let's start by looking at the angular motion. Okay? So looking at that, the only torque I have acting on my system is friction. And I know we've had trouble with this. So imagine if that were just to continue spinning and we dropped it onto the ground. the bottom part of that disc would want to slide to the left on the ground, which means the ground is going to push to the right to keep that from happening. That's why friction's to the right. So that's the only torque we have working. So we'll look at the sum of the torques. And all we have is friction times R. Plug in moment of inertia for a disk. Plug in friction. No surprises. Solve for alpha. M's go away, one of my R's goes away. And alpha is 2 mu g over R. Well, it gets me part of the way there. The next thing we're going to do is look at this as a linear object. Now, I haven't drawn it like this before, but really all that matters is that I have a force of friction pulling me forward. It's going to cause a forward acceleration. And when we're looking at it linearly, we can just pretend it's a box. I don't care about the spin when I'm looking at linear quantities. So we do the sum of my forces. We have MA equals friction, which is mu mg. So the acceleration is just mu g. So now I have what the angular acceleration is going to do and what the acceleration is going to do. If I want to find the time, I have to look at the velocity associated with each one of those. So the angular velocity as a function of time is that initial angular velocity minus that angular acceleration times time, because it's going to slow down. Friction is going to slow down that initial angular velocity. And then linearly, linear velocity is just the acceleration times time, or mu g times the time. So my linear velocity is going to speed up. Now, we want the non-slip condition, and that's when r omega is equal to v. At that time, we are no longer rolling and slipping, we are rolling without slipping, which is what we want. So we plug in our function for omega into omega, and our function for velocity into v. So it's r times omega minus 2 mu gt over r is equal to mu gt. We'll distribute that r. So we've got r omega minus 2 mu gt equals mu gt. Move that over. So r omega equals 3 mu gt. And then we solve for time. Alright, so these are some problems that may help you as you're studying for your tests. You still have to know what torque is, you still have to know everything that we've done before in addition to this stuff. I don't think it's terribly hard, but please don't neglect the study. Thanks.